All right, here we are for the second part of section 11.4, compound events. And I have up here the same slide that I had for the last video. However, in the last video we talked about what mutually exclusive means. In this video, we're going to talk about what inclusive means. Same information from the first slide. Let's go to the second slide and review. The key question again is, can the events given happen at the same time? If the answer to that question was no, we had mutually exclusive events. But today in this video, if the answer is yes, they are going to be inclusive events. Now, what does inclusive mean? Inclusive means two or more events that can happen at the same time. Okay? Two or more events that can happen at the same time. What that means is they have one or more outcomes in common. In other words, there is something in the intersection of the two Venn diagrams. Okay, so if you need to pause the video, go ahead and do that. Otherwise, we're going to look at some examples of what inclusive means and how it works. All right, example one. What is the probability that you roll one die and you get a 5 or an odd number? Well, let's go to that key question. Can both things happen at the same time? Could I roll the die once and get a 5 and an odd number? Well, sure you can. So therefore, the answer to that question is yes. So therefore, the type of problem that we are doing is inclusive. Now, how does that work as far as the Venn diagram is concerned? Oops, let's go back here. The Venn diagram works like this. First of all, what are our two desired outcomes? Well, one is the 5s, so we're going to label the first oval as all the 5s you can get. And the second number is all the odd numbers that you can get on a die. Well, let's go through them. Where would 1 be? Well, 1 is odd, but it's not a 5. Where would 2 be? Well, 2 is not a 5, and it's not odd, so it's going to be out here. The 3 is an odd number, but not a 5. The 4 is going to go out here. The 5 is both an odd number and a 5, so it goes in the intersection point, and the 6 falls into neither category. Now, if you notice, our intersection has an entry. That is why it is inclusive. There is something in there. All right, well, let's talk about the solution to this problem. What is the probability that you roll a 5 or an odd number? That's going to be equal to the probability you roll a 5. We established on the last video that or means add. So the probability you get a 5 plus the probability that you're going to get an odd number. However, if I do that, the probability that I get a 5 is 1 out of 6, plus the probability I get an odd number is 3 out of 6. That equals 4 out of 6. However, people, if you look at our Venn diagram, there are only 3 possible numbers that I can get. The answer is 3 out of 6, not 4 out of 6. That means there's something wrong with my formula. Now, why is there something wrong? Because when you deal with inclusive events, you count the outcomes in the intersection twice. And we can't do that. We counted the 5 twice. We counted it both right here, And we counted it both right here. So therefore, when you do inclusive problems, you also need to minus off the probability of both events happening. You got to subtract off the intersection point. So therefore, the real answer to this problem is the probability you get a 5 plus the probability that you get an odd number minus the probability of the intersection. Okay, well, the probability you get a 5 is 1 out of 6, plus the probability you get an odd number is 3 out of 6, minus the probability of the ones in the intersection. That's 1 out of 6, which is equal to 3/6, which equals a half, which is the correct answer to my problem. Oops, my chart is off here slightly, sorry. See if we can go back here a little bit. 1 out of 6 is equal to 3 out of 6, which equals 1/2. Okay, so let's talk union again. For inclusive events, the probability of A union B is equal to the probability of A plus the probability of B minus off the probability of A intersect B. The upside down U means the intersection. And that in green is the formula for inclusive events. All right, let's do one more example. Word problem here. There are 1,560 juniors and seniors in a school. 840 are seniors. 630 of them read the daily paper. Only 215 paper readers are juniors. Here's the question. What is the probability you pick a student at random who is either a senior or who reads the paper? So I want to know, what is the probability I pick either a senior or one who reads the paper? So again, we have to ask ourselves the key question. Can these both happen at the same time? Can you have a senior and one that reads the paper? Well, obviously that answer is yes. So therefore, this is an inclusive problem. Now comes the key, drawing the Venn diagram. All right, so in the Venn diagram, how are we going to label it? Well, first of all, we want to know if they're a senior. And secondly, do they read the paper? So that's how I'm going to label that. All right, well, let's fill in the 3 areas. How many seniors are there? Well, it says there are 840 total seniors. All right. Well, how many of them read the paper? Well, 215 paper readers are juniors. So of the 630, 630 minus 215 means there must be 400 senior paper readers. There's 840 seniors in all. So 840 minus 415 leaves me that there are 425 other seniors who don't read the paper. Now, how many read the paper that aren't seniors? Well, that's this 215 right here, because that totals up to be the juniors, which are 630. Or 630 people read the paper. I'm sorry, 630 read the paper. So there we go. We have filled in our 3 spots. So, since this is an inclusive event, what's the probability you have a senior or a paper reader? That would be the probability that they're a senior plus the probability that they read the paper. But then I got to minus off the seniors who do read the paper, so I got to minus off the probability of both of them. Well, the probability that they are a senior is there are 840 seniors total. These two numbers right here add up to 840. There's 840 seniors out of 1,560. Plus, how many read the paper? Well, that's these two numbers. There are 630 paper readers out of the 1,560, minus the ones that are both. That's the intersection point. So I'm going to minus off 415 of those out of the 1,560 students. And the grand total comes out to be 1,055 over 1,560. Now, what does that turn out to be as a percentage? Well, if you take your calculator and you divide those two numbers, it comes out to be about approximately a 67.6% chance of picking either a senior or one who reads the paper. And that wraps up inclusive compound events.